In this video, we're going to build on some earlier concepts of how to predict whether a bond will be polar or nonpolar in order to figure out whether a molecule will be polar or nonpolar. And to do that, let's start with a quick review of those ideas. So the most important thing to remember is that looking at bonds is all about looking at electronegativity to do this part. And we have this scale that if we were to measure the difference in electronegativity, which just means look at two atoms, find their electronegativities and subtract them. If we're between 0 and 0.4, we're going to call that nonpolar covalent. And a good example of that is carbon and hydrogen. So for example, right here is carbon and right here is hydrogen, and you can see that the difference in electronegativity is 0.4. That's a nonpolar covalent bond. Another option is somewhere between, say, 0.5 and 2. So we've got this big range that we call polar covalent. And up at the high end, boron and fluorine, their electronegativity difference is 2 exactly, and that's a polar covalent bond. The electrons, right, are unequally shared. And we draw an arrow to remind us of that. The tip of the arrow says where the partially negative side of the molecule is. That's where more electrons hang out. The back of the arrow, which has this handy-dandy crosshatch that looks like a positive sign, shows us where the electron deficient part of the molecule is. So the electrons are unequally shared. They like to hang out with the fluorine a little more than with the boron. Back up with our polar covalent, of course, this is equal sharing. Last but not least, bonds can tip so far into the unequal that we have at about 2.0 the formation of ionic bonds for differences in electronegativity. So I'll give you potassium with chlorine as an example. Their difference is 2.2. And so potassium really becomes potassium plus, it loses an electron because chlorine takes that electron and becomes chloride minus. This isn't sharing at all. This is transfer, which is just what we talked about with ionic bonds. Being able to do this step of looking at bonds and predicting whether they are polar or not is important. And the good rule of thumb for you to remember is that if it's carbon hydrogen or carbon nitrogen, or carbon sulfur, right? If it involves those three elements, the bonds are nonpolar. Everything else is some variety of polar or ionic. So the great majority of bonds out there are polar bonds. And of course, if they're the same, if it's carbon with carbon or sulfur with sulfur or oxygen with oxygen, if two bonds are the same, their electronegativity difference is 0, and it of course has to be polar. Let's look at how that translates when we arrange a bunch of bonds in space to make molecules, and whether molecules also have uneven distributions of electrons. So let's look at this idea of when a molecule is nonpolar. And the important thing to know is that a nonpolar molecule means electrons are equally distributed in the whole molecule, right? And one way of doing that is to have all substituents be the same with bonds oppositely distributed from one another. A good example of that is carbon and oxygen. They form a polar bond. Oxygen hogs the electrons so that there's negatives on the outside of the molecule, but this is a 180-degree angle. If we think about the carbons as being where my fists meet and the oxygens at my elbows, they're equally and oppositely opposed to each other. They're playing tug of war and completely canceling one another out. Nonpolar molecule. They are, even though there's polarity present in the bonds, it's a nonpolar molecule overall. That can happen in more complex arrangements as well. This SO3, right? These are all polar bonds. However, they're opposing one another in perfect 120-degree angles. They cancel one another out. Nonpolar molecule. Another option is tetrahedral. So tetrahedral molecules, when all the substituents are the same, Yes, all those bonds between carbon and chlorine are polar. They are all skewing towards the chlorine side, right? All of the electron distribution is going out, but it's going out in beautiful 109.5 degree opposing angles. So all of these result in a cancellation of all the polar bonds, or the dipole moments of the bonds. So these are nonpolar molecules. Now, the second we swap out one atom for another one, this stops. But right now they're in this truce. All the polarities cancel. Here's one place where I can have lone pairs and a nonpolar molecule. One more actually that doesn't involve lone pairs, octahedral, right? We've got all these perfectly 90-degree angles that result in nonpolar molecules. When all the substituents are the same and there's no lone pairs, we can cancel each other out. In one case, lone pairs can also cancel, and that is square planar. So here's a square planar molecule. And this is just one of those oddities because these lone pairs cancel each other out. They're directly across from each other. And then these chlorines cancel one another out. So this is all a nonpolar molecule. What am I looking for? I'm looking for symmetry. When it's beautifully symmetrical and everything can cancel, all the lone pairs and all the bonds, I'm going to get a nonpolar molecule. There's another way I can get them though. I can have nonpolar molecules when all the atoms are carbon or hydrogen. Because remember, CH is a nonpolar molecule, or a nonpolar bond. So it doesn't matter how wackily arranged they are. And remember from our video on structures, there are carbons wherever lines meet or wherever lines end. Carbon likes to make 4 bonds, so I count. So there's a hydrogen here and a hydrogen here and so on and so forth, or there's carbons. This carbon needs 3 hydrogens, or this carbon needs 2 hydrogens. You want to work on that translation. But when I see structures like this, when they're not specifying what the atoms are, they're all carbons and hydrogens, which means this is a nonpolar molecule. Again, the wackiness of the arrangement doesn't matter. Completely nonpolar if I have carbons and hydrogens. Let's look at the other side and talk about polarity. And one thing that's a dead giveaway for polar molecules, except for that square planar case that I talked about on the last little bit, is the presence of lone pairs. So this seesaw shape, where there's an extra lone pair here, or this T shape where there's 2 extra lone pairs, or this square pyramid where there's an extra lone pair, those are all polar molecules. Or for less complicated shapes, sulfur dioxide and water, remember, we're both bent. They have lone pairs on their central atoms. That makes them polar right then and there. Even though this is a polar bond and this is a polar bond, they don't cancel anymore. Remember, in carbon dioxide, they were arranged so that they were directly opposed to one another. In water, they're bent. And so the tug of war is overall pointing downwards. This molecule is polar, and the partial negative part is up top, and the partial positive part is down here. The hydrogens are getting left alone in the cold. A similar thing happens with the nitrogens in ammonia. You can't see it here, but remember, the real ammonia molecule has N and H, and then there's one hydrogen going back into the board and one hydrogen coming out at you, and this big old lone pair on top. Once again, asymmetric distribution of electrons. The bonds themselves aren't superpolar, because remember that if carbon and hydrogen make a nonpolar bond, and carbon and hydrogen make nonpolar bonds, then nitrogen and hydrogen is also nonpolar. But that lone pair is extra electron density. Electrons are hanging out on that nitrogen, making this side of the molecule partially negative, and this bottom part of the pyramid partially positive. Makes a huge difference with the way that ammonia behaves to have that partial positive and partial negative. So the presence of lone pairs, dead giveaway for polarity if they're on the central atom. Another dead giveaway is unequal substituents, when I lose symmetry. So for example, on this COS molecule, so it looks like carbon dioxide, but a sulfur's been swapped out. This bond is polar, and it pulls towards the oxygen. And this bond is not really polar, but it's a tiny bit polar in that direction. I mean, very tiny bit. So the bonds aren't equal anymore. You've got the big strongman bond pulling this way, and then you've got the kind of weak bond that's not doing much of anything. So overall, the molecule is polar, partially negative and partially positive sides. Similarly, when I swap out one of those chlorines for a hydrogen, they don't pull equally anymore. I've got a partial negative region of the molecule and a partial positive region of the molecule. Or those fluorines. Remember, fluorine's the biggest electron hog, the most electronegative element on the periodic table. My negative side part is over here. My partially positive part is over with less electronegative bromine. Sometimes what I do and what you need to do in your minds is divide a molecule into polar areas and nonpolar areas. So with this structure, I'm going to add the missing lone pairs that are on the oxygen. Always a good thing when you see a skeletal structure. Put in the extra lone pairs, mark in the carbons and hydrogens if you need to find them too. But now I can very clearly see that there's kind of two portions of this molecule, right? There's a nonpolar portion. And then there's a polar area where I've got the O's and the H's. And in fact, the polar part will win over 99.9% of the time. So this whole molecule I'm going to call polar on account of that tiny little OH group over there. And this is the partially negative part. And the partially positive part is kind of hanging around right here at the top of the molecule. So we keep track of those things. Being able to predict whether a molecule is polar or not is a really, really important skill. This is going to carry over into our next bits where we talk about how molecules interact with one another and with other molecules and describe why they boil at the temperatures they do, why they condense, why they form solutions with some things and not others. So practice this skill of predicting whether molecules are polar or whether they are nonpolar.